I hope that turned out. I might watch this one where it's like, the important thing, the thing you absolutely have to remember. Ow. All right, so when the methyls or the big groups are closest together, that's going to create instability. And it works out that they're closest together in the eclipse conformations. All right, so in the second eclipse conformation, this methyl and that H are close together. That H and that methyl. H and H eclipsing, the H's are so small, that doesn't really do anything. But the methyl, right, the methyl takes up some volume, and we'll see this more in the cycloalkanes, which I'll talk about in class on Thursday. We'll see how volume is what's important, not mass. Okay, so don't get carried away. When you judge stability, don't worry about how heavy an atom is. Worry about how much space it takes up. Right? The analogy I always use is like you're flying on a plane. Okay? Somebody's going to come in and get a middle seat. You've got an aisle. What are you worried about in the person in the middle seat? Their weight? Maybe. I mean, humans tend to be a fairly average. We're all pretty much the same density. Not exactly. But really what you're worried about is how wide they are. Right?
Or if they have COVID.
Sorry?
Or if they have COVID.
Yeah, okay. Yeah, if they have COVID. A lot of you have flown a lot more. My last flight was in July. It was pretty bad. Anybody here? No, I don't think I have anybody from Oklahoma, right? I'm from Oklahoma. I was flying to Oklahoma. Oklahoma is not one of these places that takes COVID all that seriously. So the people going, anyway. I was like triple masked, and I just pressed my face against the window the whole time. So what you're worried about is how much space they take up. Right? They could weigh 1,000 pounds. If they're 18 inches wide, you don't care. They could weigh 2 pounds, and if they're 4 feet wide, you're going to have a lousy flight. So what's important here is the volume of the group. Okay, a couple other things to put in here. This first one, we're going to call this anti-staggered. And the reason is the two methyls are anti to one another. They're 180 degrees apart. This is as far apart as they can get. All right? That methyl's going up and away. This methyl's coming down and toward you. The fourth structure, structure D that I drew, we're going to call that syn, S-Y-N. The two methyls are directly in front of each other. The methyls are eclipsing one another. Now we've got the two biggest groups interfering with one another. All right, this is, I'm sitting in the aisle seat, and a guy my size shows up for the middle. Right? My wife never volunteers to take the middle for us. It just never works out that way. We like to buy aisle. You know, we're the jerks who buy the aisle. When you've been married more than 20 years, you don't need to sit together. Right? It's much more important to have some space. Okay, I hope she doesn't watch these videos. We don't really have a name for this eclipse confirmation, but this next one, C, is Gauss staggered. G-A-U-C-H-E. Gauss, whatever. And in fact, what we call this I've got caps on the wrong colors. All right, so Gauss is going to be in a staggered conformation, but two groups next to each other. This is the one that tricked you guys into thinking this was really unstable, because now the methyls are closer together. And had I asked, and I should have done this again, so forget the eclipse conformations, now compare the two staggered conformations. Which staggered conformation that I've drawn is least stable? The Gauss is the least stable, because now the methyls are close enough to each other. They're not super close, and in fact for butane, those two methyls don't interact real strongly. But if you make those groups bigger, right, if we had like a butyl group and a cyclohexyl group, that Gauss interactions, the two groups will and can physically interact. Whew. All right. I did hit record again. That's nice. All right, to close out class, we're going to look at how we do conformational analysis. Okay? So, and hope maybe I'll do one more Gauss, or one more Newman projection. So we can plot, instead of just sort of saying stable, not stable, you can actually measure energy, or calculate energy, or predict energy. And energy is stability. So in these energy, you're going to see a lot of energy diagrams, and this is actually in chapter 6. If you want to kind of look over that, we'll talk about 6 kind of in detail just before we start doing chemical reactions. I'm not going to get to it yet, but if you're curious about this diagram, or when you start working more of these problems, you want some information, go look in chapter 6. Really, this is Gibbs free energy. And the way we plot this by convention is, the more stable something is, the lower in energy it is, the less stable it is, the higher in energy. And this is what's important, okay? In this class, there might be a lab. I can't remember if there's a lab we do. But anyway, in this class, all you're going to be doing is sort of predicting this structure is more stable than that structure, right? So the more stable one you should put lower. Okay, so now let's do dihedral angle. Dihedral angle is the angle between bonds. All right, so here we're going to define the dihedral as an angle between this carbon-carbon bond and that carbon-carbon bond, between C1, C2, and C3, C4. So the dihedral for the syn eclipsed is 0 degrees, right? Because they're right in front of each other. The dihedral for the anti-staggered would be 180. All right, so we know that at 180, we're going to have a minimum. That anti-staggered, where we have the 2 biggest groups anti to one another, that's going to be the most stable. If we only have 2 things coming off the 2 carbons we're looking down, having those groups anti is the biggest. 0 degrees is going to be the high point. Obviously, then we have a 60 and a 120. 60-degree rotation from staggered gets us to eclipsed. So this will take us, not that high, take us to a peak here, to a minimum, and then up here. All right? So we have our 2 staggers, eclipsed, eclipsed. And then this actually works out to be symmetrical. As an exercise at home later, do the next 2 60-degree rotations here. So again, anti-staggered is going to be the most stable. Staggered conformation, Gauss staggered will be the second. All 3 of the staggered conformations are going to be lower in energy than the 3 eclipsed conformations. All right, 2 minutes left. 2.5 minutes left. Honestly, I'll give you more time in a few weeks when you've practiced it. So I'm not going to ask you to do it. Let me just draw the Newman projection you would get for this, the 3-chlorooctane that's got the chloride in front. Okay? So my I is here. You have to define a front carbon. I'm going to put a little circle around that. Same thing as in the butane. I've got a methyl that's down. That doesn't always have to be the way it is. It's just how it's turned out here. What are the other two things on that circled carbon? Hydrogen. We got two hydrogens. And again, that is an sp3 carbon. One H is going to be to one side, the other H is to the other side. sp3 carbons in a Newman will always look like this. Lines 120 degrees apart. All right, so then the back carbon, again, let's put in our bonds on the back carbon. I'm going to draw a staggered conformation, but it really is. And this is why you've probably noticed hydrocarbons tend to be drawn in this zigzaggy way. And the reason is that gives us a staggered conformation, and it usually, or it often, puts the biggest groups anti to one another. All right, so if I'm looking down this way, the back carbon has an H down to the left. It's got a chlorine down to the right. All right, this chlorine, if I'm there, the chlorine's out in front of the board. If my head's on the board, the chlorine is to my right. And then up, there's a CH2. You have to fill in enough information to get this entire molecule. 1, 2, 3, 4, 5. You can write C5. That differentiates it from any other group. That's enough, really. But if I don't have this picture, I need to know what else is there. And so this would be C5H11. Or you can just draw the molecule at this point, right? So 1, 2, 3, 4, 5. I know that was fast. Let me ask you this. Is there a more stable Newman projection for this?
I'd say yes,
Why?
because I feel like we can find a way to put the chlorine and the C5H11 farther away from the CH3.
You actually can't.
You know?
But that would be what you'd want to do, right? So here, methyl is anti to C5. It's gauche to chlorine. So what you have to figure out is the chlorine or the C5 group bigger. Right? Chlorine's a bigger atom, but it's one atom. All right, go back to the plane analogy. You'd rather have one like guy my size in the middle seat than a family of 6. If you can imagine. It'd be like squirrels or something. All right, so the chlorine's actually smaller than C5. This C5H11 group is going to carve out an enormous volume. So this is actually going to be the more stable it could be. If I switch the chlorine and the H, let's do this one last thing. I know I'm over time. So over on the other, right, if I switch the chlorine and the H, C5 is still up here. What am I doing? I've just switched the chlorine and the H, right? Okay, so you guys need to practice drawing Newman projections. You need to practice looking at molecules. Don't do too much in your head as you do this. Think about conformations and all that stuff. On Thursday's class, I'll do another little bit of this if you want to see that, and then I'm going to do cyclohexanes, so go ahead and look at that. If you're coming to class Thursday, look at cyclohexanes. Those of you here today, Thursday morning, I'll send out an updated, like, who can come, because, there's a lot of folks that can't come to class. So, and I will do something for you guys, like a Zoom meeting at home. All right, say hi to your classmates. You're in class with these people.